welcome again. Now, I will discuss diode resistance and capacitance. This is lecture 3 and the topics are diode resistance and diode capacitance. Diode resistance and diode capacitance. This means there are two types of behavior, resistive behavior and capacitive behavior exist in p-n junction diode, and how it is exist I will discuss. First of all, diode resistance. What is diode resistance? Basically, this is the resistive behavior, and there are two types of resistive behavior under the presence of AC signal and under the presence of DC signal. And this means there are two types of diode resistance. The first type is called DC or static resistance, and the second type is called AC or dynamic resistance. Now, DC resistance. The application of DC voltage to a circuit containing semiconductor diode will result an operating point on the characteristics curve that will not change with time. The DC or static resistance of the diode at the operating point is defined as the ratio of voltage across the diode to the current through the diode. This means static resistance is the nothing at the operating point. The ratio of voltage across the diode to the current through the diode is called static or DC resistance. I will discuss it with the help of graph. This is the p-n junction graph. Here you can see this is the forward characteristics of p-n junction diode. Here this is the curve. Suppose this is the operating point, this is the Q point. If we want to know the static or DC resistance, what should we do? Just we have to take the values of voltage across the diode and current through the diode. Yes, when we will draw a perpendicular, this is the voltage across the diode because x axis is the forward voltage, and at y axis this is the forward current, and we will draw the perpendicular, this will become the current. And what will? The current is 75, we can see that here 75. The current is 75 milliampere and voltage is 0.75 volt. This means the forward voltage or static resistance, this is the static resistance or DC resistance. This is equal to 0.75 volt upon 75 milliampere. This is equal to 10 ohm. Yes, the operating point is here. Suppose this is Q1. Yes, we have taken a point Q2 here. Q2 is the operating point at high current, higher current. What will happen here? When we will draw perpendicular, this will become voltage and this is current. Here voltage across the diode is 0.875 volt and current through the diode is 175 milliampere. Now, it is become 5 ohm. This means the resistance decreases. Why? Because at high current the conductivity of the diode increases, that is resistance decreases. This is not a new thing. At lower current, the less current, this means resistance will increase. This means at lower current resistance is higher, at higher current resistance is lower. This is the reverse process. This means resistance and current, these are the inversely proportional according to the Ohm's law also. So, this is all about the DC resistance. Now, if we want to calculate a DC resistance or static resistance in reverse bias, how we will calculate? We have learned to calculate the DC resistance in forward bias. In reverse bias, it is simple. First of all, like this. This is reverse voltage, this is reverse current. Suppose this is the reverse bias characteristics and the operating point Q is here. This is the operating point Q. Then what will happen? We will draw a perpendicular to here and perpendicular here. Suppose this reverse voltage is the minus 30 volt and this is the 1 nano ampere. Then DC resistance RDC . RDC is defined as the minus 30 volt upon minus 1 nano ampere. This is equal to 30 into 10 के power 9 ohm. This means 30 giga ohm. Wow! The resistance is very high. In reverse bias, you can see that resistance is in order of giga ohm. This means this is like open circuit, infinite resistance. That is why in all approximations, in all ideal or practical diodes, in reverse bias diodes are open circuited. Why it is open circuited? You can see here. The resistance is in order of giga ohm. This is the reason that I have also taken an example in reverse bias. Now, AC resistance. What is AC resistance? AC resistance is defined as the change in voltage across the diode to the change in current through the diode. This is the application of AC signal, and how we will calculate the AC resistance. Just this is the operating point, and there are 2 points taken at the same distance. At one point is at the up side and another point is at the lower side, and we will calculate the change in voltage and change in current, and by taking the ratio of change in voltage and current, change in current, we will get the AC resistance. And just for an example, this is the graph. There are 2 points. Here, suppose this is the operating point Q. This is operating point Q. Then we have taken 2 points at upside and another point is at lower side, same distance. Now, this is the change in voltage delta V, and this is the change in current delta IT. Then by taking this 0.875 minus 0.75, the change in voltage, and change in current 175 milliampere minus 75 milliampere, and this is equal to 1.25 ohm. 1.25 ohm. This is very less resistance. It is the example which have been taken in forward bias. If we want to calculate the AC resistance in reverse bias, we can easily calculate the resistance in reverse bias by taking the 2 points. Okay? Then like the resistance will be very high. Why it will be very high? Because the current will be in order of nano ampere or micro ampere. So, we can easily calculate the AC resistance here also. Suppose I have taken this point. Now, if there are 2 points, this will be change in voltage and this will change in current. This is the change in current. Then RAC is equal to change in voltage upon change in current, and this is will be equal to in order of giga ohm. Okay, guys, because the current is in order of nano ampere, like in case of we have seen in the DC resistance also. Now, we have seen the resistive behavior. We have seen the resistive behavior. How it is beneficial in any numerical. Suppose there is a rectifier circuit. If there is a resistance given, suppose forward resistance is 10 ohm rectifier circuit, then we will replace the diode 0.7 volt and series resistance 10 ohm. This is called AC resistance. So, the application of resistance will be in case of diode circuits, we will see later. Now, capacitive behavior. This is the very important behavior, capacitive behavior. How capacitive behavior arises in semiconductor diodes or any semiconductor device. It is also happen in transistor, MOSFET, JFET. In every semiconductor device there are capacitive behavior. So, first of all we should know ki what is capacitive behavior. All of us know that when there is a storing of charge at rest, जब भी कभी चार्ज स्टोर होता है और वो रेस्ट में होता है, तो दिस इज कॉल्ड कैपेसिटिव बिहेवियर. So, there are two types of capacitive behavior in semiconductor diodes. One is the transition capacitance or space charge capacitance, and another one is the diffusion capacitance or storage capacitance. There are two types of capacitance. Now, first of all, transition capacitance. It is very interesting. Guys, all of us know that in case of reverse bias, there is a depletion layer, and in depletion layer at the end side, the positive immobile ions are there, and at the p side, negative immobile ions are there. This means these ions are at the rest, and these rest charges will behave like a parallel plate capacitor, like this. Suppose this is a plate, and it is positive and it is negative. So, here these are the negative charges and these are the positive charges. This will behave like a parallel plate capacitor, and all of us know that the parallel plate capacitor is given by A epsilon by D, where A is the area of cross section, epsilon is the permittivity, and D is the distance between the plate. So, this is the analogy, parallel plate capacitor analogy. This means the depletion layer of the diode will behave like a parallel plate capacitor, and the transition capacitance, which will due to the depletion layer, transition capacitance is given by Ct is equal to K upon Vk plus Vr whole raised to the power n, where K is the proportionality constant and Vk is the knee voltage, and Vr is the applied reverse voltage. We can simplify it. Suppose this is the K and Vk is taken as common. Here it is 1 plus Vr upon Vk, and Vk raised to the power n, this is raised to the power n. And now, at reverse voltage is equal to 0, at Vr is equal to 0, suppose this is C naught, and what will C naught? C naught is K upon Vk whole raised to the power n, when we take Vr equal to 0, and this is called C naught. This means Ct can be written as C naught upon 1 plus Vr upon Vk whole raised to the power n. This is the graph of this is the equation of transition capacitance. Very simply, transition capacitance, where C naught is the K upon Vk raised to the power n. Yes, what is n? N is a constant. The value of n is 1 by 3 or 1 by 2, depending upon the types of semiconductor, where it is heterogeneous or where it is homogeneous. It will be given by the examiner when it will be asked. Now, what is the graph? The graph is like this. Transition capacitance. Here it is the reverse voltage. Reverse voltage is in volts, and it is the y axis. This is the transition capacitance, and transition capacitance in picofarad, and this is 0. At reverse voltage 0, the value of capacitance is C naught here. This is the C naught. At reverse voltage tends to infinity, the transition capacitance tends to 0. This is the graph of transition capacitance. Ct is equal to C naught 1 upon Vk upon Vr Vr upon Vk whole raised to the power n. This is the graph of transition capacitance. This is the transition capacitance. Now, another type of capacitive behavior. Another type of capacitive behavior is the diffusion capacitance. How diffusion capacitance arises in p-n junction diode? this is due to the diffusion of majority charge carriers. This means this capacitive behavior is dominant in forward bias. This capacitive behavior exists in forward bias. When diffusion of majority charge carriers occurs, this means when electrons moves from the n side to occupy the holes at p side, these electron stores there and wait for some time to occupy the holes. This means the rate of movement, the rate of diffusion of majority charge carriers is greater than the recombination of electron and holes. This means if this process mismatch, this means there will be a storage of majority charge carriers, and these storage of majority charge carriers happens due to the mismatching of diffusion and recombination, and separation. Okay guys, this capacitive behavior is much larger than that of transition capacitance, and that is why this is called storage capacitance, and storage capacitance is proportional to the diffusion rate. This means this is the proportional to the forward current, that is diode current, and it is also proportional to the relaxation time tau. If tau is greater, this means storage, the majority carriers has to wait for more time. This means this will store for more time. This means this is simple, that storage capacitance or diffusion capacitance is proportional to the relaxation time as well as it is proportional to the forward current, and CD is equal to tau ID upon Vk. This is the diffusion capacitance. Now total capacitive behavior, the total capacitive behavior is equal to, this means this is equal to Ct plus Cd, where Ct is the transition capacitance and Cd is the diffusion capacitance. How it will act like that? All of us know that in parallel combination, this is like that. There are two types of capacitive behavior. One is the Ct and another one is the Cd, like this, parallel. This is Ct and this is Cd. So that this is the addition of these two, total capacitive behavior. If we want to draw the applied voltage versus diode capacitance graph, we can easily draw it like this. Y axis, this is the capacitance, x axis, negative x axis reverse voltage, positive x axis forward voltage, and this is like this. Here dominant diffusion capacitance, C diffusion, and here transition capacitance, and C is equal to Ct plus Cd. Okay guys, and this is 0. This means in forward bias diffusion capacitance dominates, and in reverse bias it is transition capacitance, and Cd is greater than Ct. So we can say that total capacitance is approximately equal to Cd, because Ct is very less, and this will also be discussed in special purpose diode. When I will discuss varactor diode, then we will also discuss what is the capacitive behavior in varactor diode. Now this is the graph already I have discussed. This is the diffusion capacitance and this is the transition capacitance, already I have discussed. This means why it is required to understand the capacitive behavior of diode. What is the physical significance to understand the capacitive behavior of diode? Guys, all of us know that in any electronic circuit or electronic appliances, there is a circuit of switch on and switch off. All of us know that when we will switch off the TV LED, the एलईडी ग्लोस फॉर सम टाइम, हम लोग पावर सप्लाई ऑफ भी कर देते हैं तो भी एलईडी कुछ टाइम के लिए ग्लो करता है। मैं पूछूंगा क्यों, तो द आंसर इज सिंपल दैट देयर इज अ कैपेसिटिव बिहेवियर। जब भी किसी सर्किट में कोई कैपेसिटिव बिहेवियर होता है तो वहां पे चार्ज स्टोर हो जाता है, और अब जब आप सर्किट को पावर सप्लाई से अलग कर देते हैं तो चूंकि वहां पे पहले से चार्ज स्टोर था, देयर इज ऑलरेडी स्टोर्ड चार्ज एंड दैट चार्ज विल डिस्चार्ज, तो जितने समय में वो डिस्चार्ज होगा वो आपको एलईडी ग्लो करता हुआ दिखेगा। तो ये एक कैपेसिटिव बिहेवियर का एग्जाम्पल है। ऑल ऑफ अस अंडरस्टैंड द फिनोमेना ऑफ कैपेसिटिव बिहेवियर इन एनी डायोड, एनी सर्किट, दिस फिनोमेना exist. Okay guys, now, okay guys, thank you.